Why is this quarter so easy to blow over? But this quarter, not so much. Why is this so easy? And this, not so much. Why is this so easy? But yet this, not so much. There is a mysterious force that inhabits spinning objects. They can defy gravity. But is this force really so mysterious? These puzzling effects live at the intersection of angular momentum and Newton's first law, which is inertia, and Newton's second law. You have to apply a force to something to change its velocity, and you have to work to make it stop moving. I'm going to explain to you that if you believe Newton's first law, that moving objects like to keep moving, these weird gyroscopic effects are actually pretty easy to understand. And then I'm going to tell you how important this effect is for a million real-world applications. In any event, I like to think of moving a spinning object as not that much different than trying to change the course of an object moving in a straight line. If I need to bat down one tennis ball to make it stop, it's not that hard. On the other hand, if I have a cannon shooting one tennis ball per second, it's more work, because a new tennis ball is coming by every second. What if we had a continuous stream of tennis balls? A jet of water is like a continuous stream of balls of water. Ever notice how it's easier to rotate a non-flowing water hose than one that has water shooting out? Well, the reason for this is that for the shooting water, as you rotate the hose, you are bending it in front of the stream of water balls, forcing each new ball of water to change direction. The faster the water is moving, or the more water there is, the more work you have to do. Now do you know why it takes 2 firemen to safely operate the hose? Now let's take our spinning tire. Imagine the tire broken up into a bunch of narrow tire wedges. And let's take the wedge that's in my same plane as my axis of rotation. I've drawn a tunnel around it. When I try to turn the still tire, I am only moving that single tire wedge to maximum deflection. On the other hand, when my tire is spinning, while I am tilting that tire, there is a continuous stream of my tire wedges moving through that cross-section point. I have to bat each one of them down as it passes through my tunnel, just like batting down a constant stream of tennis balls. So bending those wedges moving through this point is kind of like rotating the fire hose with the water moving through it. Do you think the mysterious stability of the spinning gyro is a mystery? Nope, it's just Newton's first law. The natural resistance to a change in the motion, which is called inertia, applied to a bunch of masses trapped in a circular motion. Do you think this is just elementary physics? Well, you're wrong. Richard Feynman started thinking about the movement of spinning plates when he saw it done as a trick. He developed new mathematical approaches to solving such problems. Their application to the movement of subatomic particles led to a Nobel Prize. Do you think gyroscopes are just toys? Well, you're wrong. Guess what? It's not just tricks that are the applications. In sports, in a football, throwing a football with a spiral improves distance and accuracy. In hockey, a spinning puck makes the shot faster and more accurate. In cycling, speed keeps the bicycle upright. And it's not just sports. You can see the gyroscopic effect in many real-world applications such as satellite positioning, inertial guidance systems, enriching uranium, medical imaging, and you can also see it in the pursuit of pure science such as subatomic particles research, planetary dynamics, and quantum physics. As you can see, the gyroscopic effect is actually pretty simple when you think about Newton's laws.